Uh, Thank you for the introduction. Thanks a lot for inviting me for organizing the workshop. This talk is going to be about a different clustering algorithm, one that we haven't seen yesterday. And it's also going to be about bridging theory and practice. So we're taking a theoretician's approach to a problem that I think has not received as much attention in the theory community. I wasn't sure how to illustrate, so I added generative AI. I guess this is theoreticians and practitioners on both sides of this bridge and construction. I realized today in the morning it's not the best illustration because I like to think that there are people actually in the intersection of those two communities, and there are not too many in this picture. But still, it's a topic I care about a lot, and I would be discussing later on. Let me start by acknowledging my amazing collaborators. I know that some of them may be in the audience. I saw Kishan joining yesterday remotely. And yeah, this talk is about clustering. We all know what clustering is. It's a broad class of problems where the input is a set of points. We would like to output a partition of those. And it's a problem with lots of different applications, starting from the obvious one of deduplication, through things like community detection. The input is a social network. You would like to find communities, through some less obvious like object tracking and many more. Now, I do care a lot about different applications of clustering. I work in a research team which is actually building a clustering library. We have over 100 different use cases within Google. And in this talk, I'm going to focus on a particular class of algorithms that I think is by far the most widely used. So something that's very broadly applicable. Now, a big challenge that we face is how to obtain high quality clustering of very large data sets. Think of billions or tens of hundreds of billions of data points that you would like to cluster and obtain very good quality. So there are lots of different clustering algorithms. We all know that. This is a picture from scikit-learn, a Python library that contains lots of different choices. We have, and then we have many different choices. The inputs to the clustering can be either a set of points in a metric space, or what I'm going to assume in the talk today, a set of vertices in a graph, and the edges of the graph are going to give us the similarity between the two endpoints. And specifically in this talk, I'm going to focus on agglomerative clustering, which is illustrated here. You can see that it's doing pretty well. I mean, it's what its output looks pretty reasonable. It also works very well in practice. It delivers the vanilla version delivers excellent quality clustering. Why work with graph clustering and not metric space clustering? Well, there are several reasons. So the graph clustering can actually solve metric space clustering. When you have a selection of points in a metric space, you can build a graph that represents that metric. A pragmatic choice is to build like a k nearest neighbor graph. So for each point, you connect it to k nearest neighbors in that space. You typically use k, which is low, so that your graph is sparse. This is in practice. This is not really limiting the quality. And then this way you obtain a modular design. So finding distances in very large data sets is actually a computationally hard problem. Clustering is also non-trivial. We have this separation. You can decouple and analyze both pieces in isolation. And it also graphs allow expressing more complex notion of similarity. So a very common approach is to have embeddings that you want to cluster, and then distances between those embeddings, which naturally means that the underlying similarity metric is a proper metric. It has triangular inequality, but actually it has been observed that that similarity, some say machine learning models that are not restricted to triangle inequality, for example, cross-attention models, they can provide higher quality similarities, and then those are naturally represented in place. All right, so what's the plan for this talk? Well, we're going to start with like hierarchical agglomerative clustering in the exact sense. We're going to show sequential algorithms and some hardness results. And then we're going to discuss how these hardness results can be bypassed if we allow approximation. All right, so let me first define the algorithm. It's extremely simple. It's maybe the most natural clustering algorithm you can think of. So the input is a weighted graph. The edge weights denote similarity. So the higher the edge weight, the more similar the endpoints are. And now we start by putting each vertex in its own cluster. And as long as there are at least two clusters, we find a pair of the most similar clusters. we merge them together. Merge means we replace them by the unit. And then we repeat as long as there are at least two things to merge. Yes.
So there's an immediate question here. You define similarity on pairs of vertices, but as soon as you start this, you have sets of vertices rather than single vertices. How do you define
That's an
similarity?
excellent question that I have right here on the slide. Yes, I will get to it in the next slide. Yes, and there's actually a second question. The second thing I haven't said, there is no output here, and this is also something I'm going to define in like 2 slides. Any more questions about the definition? It's underdefined, so yeah. Let's share more details. Yeah, so how is similarity defined? When we have point-to-point similarity, it's just the edge weight. But what about what happens when the clusters grow? Well, throughout the stock, we have 2 clusters, and then the edge weights between those clusters are W1 to WK. And then I use this notation to denote the size of the clusters. I'm going to use the following notion of similarity. This is the so-called average linkage similarity, and that's the sum of the edge weights between 2 clusters divided by the product of their sizes. Why do we divide by the product? Well, the product of the 2 cluster sizes is the maximum number of edges we can have between them. So this is just like, this is equivalent to assuming that every non-edge is a pair of similarity 0. Now, this is just one way of defining the similarity, but it's interesting both from theoretical and in practical perspective. In other notions of similarity includes, for example, single linkage, in which case you take the maximum of those weights, and then the problem becomes very similar to MST. It's actually pretty easy to solve in various settings. Now, average linkage has been observed to deliver better quality, but it's much more challenging to analyze because of this averaging that happens here. The computational complexity is, as we will see later, much higher. And then, of course, there are things you can do, things like median and so on. I'm not going to talk about those. In this talk, throughout, I'm going to assume that this is the similarity that we work with. And the second thing is, what is the output? Well, the output here is a dendrogram. So it's a tree that represents all of the merges that we make. The leaves of this tree represent individual points, and whenever we merge 2 clusters, we add a new vertex with the children representing the 2 clusters. So every leaf here is cluster of size 1. Every internal node is cluster of size more than 1. Actually, the size of this cluster is the number of leaves in the subgroup. Now, once you have a dendrogram like this, you can actually, once you compute it once, you can turn this into flat clusterings by just cutting this tree at like a level that you would like to choose. You can control granularity, and then you can restore a flat cluster from that, such as a partition of input data. So now the algorithm is defined. Are there any questions? What problem? Yes, this is a very good question. Yes, so I think I don't have a good answer. I mean, this is an algorithm which delivers excellent quality in practice, and it's particularly good for deduplication. Whenever you have like whenever you know what similarities between the individual data points. It's very good whenever you want to have clusters of like average size that's very small. So think of like a power law distribution of cluster sizes. The average cluster size is like, say, constant. In terms of what objective it optimizes, I think there is no good answer for this question. I mean, I don't know if others may be able to comment, but I don't think there is anyone was able to come with an objective that this algorithm exactly optimizes.
Yeah, it's a one. I mean, in fact, when you say, "Oh, this produces clusters of good quality," I was wondering how you mentioned quality.
Yes.
You mentioned a couple of these things.
Yeah. So, well, I think this is all those quality measurements are empirical. So you sample a set of pairs of data points. You send, say, 10,000. You send them to human raters. You get your verdicts. You use those labels to compute precision and quality. And yeah, and this algorithm in like some studies we did was giving the best results that we were able to obtain. Now it's an amazing, but it's a great question. What it actually optimizes for, we do not know, and it would be great to have like a theoretical objective that we could use as a proxy, we don't have one. Yes, Samir?
My understanding is that at least people in biology who are trying to reconstruct the tree of life. They actually have some measures and then they try to say, I observe the current species, I want to know how they evolved. And then they have some biologists who study different species and say which splits happened before other splits based on some data, and that's kind of how they try to evaluate the quality of a particular.
So I think that's morally similar to the thing that I said, that you have some ground truth and you would like to you'd like your clustering to be as similar to the ground truth or some labels as possible. Yes, Martin?
So isn't this connected to this ultrametric embeddings that you can embed whatever they have in handling data to ultrametric, the flow distortion in this algorithm intelligence?
I'm not familiar with this connection. I'm not sure I can comment.
Vincent at Loadings.
Yeah, we can discuss offline, but
Yes, how, I mean, when you have this average linkage, I guess in practice, I don't know, so you can analyze them to time. This thing, so like if you solve it like the optimal, like still find the best. There's CND, find like near optimal, like what is speed it up. Is it going to be so like robust? So like I don't know what it means. You get a near similar solution or high quality empirically, as you said, even if you don't believe it. That's difficult.
Yes, so all of those are true. Yes, so solving it exactly is going to turn out to be difficult. Solving it approximately is going to be easy. Adding some relaxing this condition that we merge the nearest is in practice not going to affect the quality by so.
Just to confirm, a way to measure the quality, the first one that you mentioned is about some downstream application. You compare different algorithms and in the downstream, this one is better.
Yes.
This is Thank you.
Oh, lots of questions. I like that. So, any more? All right, let's move on.
But better in terms of what? Human perception of the.
I mean, and there are, of course, in applications, there are multiple levels, right? You have some synthetic metrics, like say if for a human, is this clustering better than that one with respect to some decisions on whether these two pairs of nodes should be in the same cluster or different clusters. But then there is the final evaluation in application. Whatever application you have, you can measure some metrics and that's like entirely application dependent.
Yeah.
All right, so let's see an example just to make sure we're on the same page of how this works. We have a graph. We start with clusters of size 1. We find the pairs of cluster of highest similarity. We merge them together. Now these two clusters have the highest similarity, so we merge them together. And now what happens is that similarity of the middle cluster, the top one is 0.5 divided by the product of the cluster sizes. That's 1/4. And here the similarity of the two bottom clusters is 0.9 is the sum of the similarities. 4 is the product of the cluster sizes, and that's the total similarity. Next merge is going to use the green edge. All clear? All right. So before I move on, let's slightly change the way we look at this algorithm. Nothing's gonna, it's just gonna be more convenient for the description. Instead of looking at a graph and clusters that grow, we will be looking at a graph where all the clusters are contracted to a single vertex. So let's define a graph H where each vertex is a cluster. We have edge between two vertices representing clusters. If there is an edge between those clusters in the graph, and then the edge weight of this graph H is going to be cluster similarity. So just a simple example. This is the original description. This is the one with contracted clusters. Here we don't have any clusters. Every vertex is a single cluster. Again, we find two vertices and we have to merge them together, which corresponds to merging the clusters. Nothing is really happening here, but this language is going to be more convenient for the descriptions in the following. And now these two clusters merge, and then we have this graph. And essentially in each step, we contract the highest weight edge in that graph. And then we need to update the edges of the incident, weights of the incident edges. And this interpretation of the right is the one I'm going to use in what's following. Okay, so now the question is, how fast can we implement this algorithm And then we looked at this problem. Previously, this problem was only studied in matrix spaces, so it was possible to run this algorithm in quadratic time, which was in a sense optimal because that's the input size. Now we observed that actually, if we assume that the number of non-zero similarities is m, so that if we work with an input which is a graph of m edges, we can run this algorithm faster in n square root m time. And let me now explain the high-level idea. So the algorithm that achieves this n root m time maintains this graph h explicitly. Now, and then we would like to store the adjacency list of any vertex in a max heap so that we can efficiently extract the max weight incident to any vertex. Now, the problem is that when two vertices x and y merge, all those edge weights have to be updated, right? Because now the size of this merged cluster is changed, so all those edge weights have to be updated. That takes a lot of work, and that very easily leads to quadratic problem. So in order to deal with this problem, we use the following approach. I'm gonna skip over one step. So one can actually, without loss of generality, say that it suffices how to efficiently support n merge operations and n queries for the highest weight edge incident to a given vertex. And if we can implement both of these operations efficiently, we can also implement the whole algorithm. And now to implement these two operations, the main idea is to direct the edges of H such that each vertex has square root of m outgoing edges. Such a direction is always possible. You can sort vertices of your graph from like highest degree to lowest and direct all the edges back to the back. You can see that this ensures that the out degree of each vertex is square root m. And you can also maintain such an orientation dynamically. Actually, you can maintain it in low update time and with low number of switches of the direction. Now, for a vertex, we're going to store only the weights of its incoming edges in a heap. So we don't have a bound on the number of those edges, but these are the only ones that we're going to store. And now when two vertices merge, well, what needs to happen, we have to merge the two heaps. That's doable efficiently. But we also need to notify all of the out neighbors, but they're just square root of m. Only those need to be notified about the change so that they can update their data structures. And when we want to query for the maximum weight incident to a given vertex, we can query the heap, and we also need to inspect one by one the edges of the remaining square root of m edges, and this way we get the n times root m running. All right. I see people nodding.
Could you do this even faster if you assume that the graph had bounded diversity?
Great question. The answer is no, because you need not just bounded diversity for the initial graph, but also for each graph you encounter along the way.
So once you contract, it doesn't have.
Yes.
Okay.
So imagine you have a graph with large diversity, and you insert a vertex in the middle of every edge. Now your graph has constant diversity, but it has a minor which has high diversity. So, but if you have a planar graph, yes, because every minor of a planar graph has constant diversity, and this algorithm runs nearly linear time on like planar or minor classical graphs. All right. So now, still, that approach doesn't seem to work. But there's a question of, can we do this faster? It turns out the answer is it's unlikely. So it turns out that running hack in time n to the t, even for sparse graphs, can solve triangle detection running in times n to 2t. And then basically the consequence is that if we could run hack in times less than n to omega over 2, we would have a breakthrough for triangle detection. And if we could run this combinatorially in time less than n to 1.5, we would have breakthrough for combinatorial triangle detection. Now, this first point leaves some space to improve the algorithm, except that it's entirely unclear to us how to take advantage of multiplying matrices of size through that to speed up this algorithm. So our hopes for speeding it up are not high, but it will be amazing to see some application of class matrix multiplication.
So, yeah. The second point is into the 1.5 more or less. And your current algorithm is still like n squared.
It's n root m, right? So
Right.
for sparse graphs, yeah. For sparse graph, they map.
Got it.
And sparse graph are essentially like the most important, yeah, in base here.
But like for dense graphs, potentially possible here. Maybe plus n.
Yes, this may be, yeah, I think that the whole, along the trade-off, it may be possible to. Okay, so then we studied the hardness in the sequential setting. We also studied it in the parallel. Yes.
Are these ideas similar to those used for when you are working with metric instead of similarity?
In terms of.
I mean, because I think you mentioned that for similarity, you are not for similarity, for a metric, you already had this sub-quadratic time. Is it true? No.
No, for metric, the time is quadratic and it's actually like.
Because the input.
The input is
okay,
quadratic.
let's do some kind of assumption. Oh, okay, that's fine.
Now, when we assume here, we assume that the input is as potentially
Yeah,
positive.
the zero.
So we also look at whether we can parallelize this algorithm, and it turns out that this problem is P-complete. We can actually evaluate Boolean circuits using average linkage hack, and cluster all the gates that evaluate the true with some special vertex, and also for gates that evaluate the both. More recently, we learned it's actually even harder than what we thought. It's CC hard. That's yeah, that's another complexity class for parallel algorithms, even on trees of diameter 4. So even on those very simple instances, we can't really hope to parallelize. There is one case where we can have a parallel algorithm. That's when the input is a path. Not that anyone cares about clustering a path, but even this algorithm is actually not trivial. We spent good amount of time thinking of how to do this, and this is just to show that there are some graphs where you can do it, but they're actually not too interesting. All right, so we saw an algorithm in the sequential setting. We saw a lot of hardness results. So the question is, what can we do now? Well, the answer is that we can do better if we allow approximation. Now, probably half of you are wondering, what is approximation if I have a problem with no objective? But that's actually exactly what it's exactly what Robbie suggested. We actually, well, we say approximation, but what we actually do is we allow slack in how we choose the pair of clusters to merge in a stack. So instead of insisting that we merge the two most similar clusters, we are allowed to merge any two clusters that are 1 plus epsilon factor from the most similar ones. All right, and now let's see how this quite easily gives us a faster sequential algorithm. I mean, I'm gonna jump over a lot of details. Again, we maintain the graph H, we store all the edges in a heap. The hard case here is that a node X merges with node Y. Y has very large degree, and X and Y have no common neighbors. Why do I say no common neighbors? Well, if two vertices have common neighbors, then after contraction, the number of edges in the graph goes down, and I can use that to charge to pay for the work that I did. So let's assume that you have no common neighbors. Canonical example is when it's a star center at Y. Something merges into the star center, all the star edges need to be updated. Well, what are we going to do here? Well, we're going to do a simple thing. We're only going to update weights of edges incident to Y when the size of the cluster represented by Y increases by 1 plus epsilon factor. So we're not going to exactly maintain the correct edge weights, but you can see that if we only do this recomputation every time the cluster size increases by a constant factor, we're going to be off by this constant factor, and because of the approximations we allow, this is still going. So that's the high level idea. This immediately gives us a near linear running time for a cluster. So this was easy in the sequential setting. It becomes a little harder if you want to parallelize that. So we introduced parhack, which is which is a shared memory parallel hack algorithm. And this algorithm, let me now give you a brief overview of how it works. I'm not going to go to very deep into technical details, but just to show you some of the challenges involved when we get in given the algorithm. So the algorithm runs in stages. In every stage, let M be the maximum edge weight in the graph. And now we know from the definition of the algorithm that each edge of weight at least M divided by 1 plus epsilon can be contracted. That's fine by the updated definition. Now we can also observe that any matching consisting of edges of weight at least M divided by 1 plus epsilon can be contracted in parallel. Right? I mean, those matched edges, when they contract, they don't interact with each other, so this is still fine. But of course, that observation alone does not suffice. If your input is a star, any matching has size 1. So we need to do more than just that. All right, so the goal of the stage is to ensure that we have got rid of all the edges in the graph of weight more than M divided by 1 plus epsilon. You can see that as we contract edges, the edge weights can only go down. So once we're done with the stage, you will never get edges of weight more than M divided by 1 plus epsilon. And then, of course, if we know how to do a stage, the number of stages is just going to be better. Where in the number of vertices and the aspect ratio. All right, so what's the idea behind a single stage? We randomly color vertices red and blue. We only consider edges that are heavy enough to qualify for this stage. And then we have an algorithm for merging blue vertices into red ones, such that we can merge multiple blue vertices into a red one, as long as the size of the red vertex, or the cluster represented by it, does not grow by more than a factor of 1 plus epsilon. So the way this works is that we randomly color vertices, and then each blue vertex is going to try merging with a randomly chosen red neighbor. And now the analysis, and then the red neighbors receive the proposals and they accept as many as they can until their size grows by 1 plus epsilon. And then the high level analysis is that either a blue vertex is able to merge with some red vertex, and that's good, we make progress, or the other option is that it's not able to merge, and in that case, intuitively, it means that most likely constant factor of my neighbors have grown by a large factor. But that's also some kind of progress. In both cases, I could show that the algorithm is progressing. Like in the latter case, the blue vertex and expectations will lose half of its incident edges. And we can use those, we can use these two scenarios to argue that the algorithm runs in polylogarithmic rounds. There's like the log number of logical rounds and then another log number of rounds to actually implement this in like a parallel model like Hierarchical or work. All right, we actually implemented this algorithm and it's turned out to be fast. I mean, it should not be a big surprise that a parallel near linear time algorithm is faster than quadratic one. This is what you see essentially in the picture on the right. And we're actually able to scale this algorithm to run on 100 billion edge graphs in about 3 hours. So this was very good. I mean, this was a big step ahead from the quadratic algorithm that cannot handle data sets of anywhere near this size. But it was still not like a fully satisfactory answer for us, even though we got polylog number of routes and the algorithm is reasonably efficient on a single machine. We still, yes.
So as in the experiment before, in this plot, you actually used a lot of processors and you measured like the elapsed time.
Yes, so this is using, I believe, 72 cores, and we measured the running time of Hierarchical compared to fast cluster, which is the N-square algorithm that was known before.
Just sequential.
That's sequential, yeah. And then there is also a seek hack. This is the approximate hack, which is also sequential. So, okay, so let me discuss this. So this was the quadratic time algorithm. This is log scale. Then we had got the first improvement with the sequential algorithm that's approximate, and that was near linear time. And then we improved this to a parallel algorithm with Hierarchical. Hierarchical here is actually computing the k nearest neighbor graph from a metric space plus clustering, and this bottom line is just the clustering.
terms of quality, it was, the results were good.
Yes, I wasn't sure how much time I have, but actually maybe I can, let me jump. No, I think I have 30 minutes, right?
Only an hour to talk, so yeah, everything's.
Yes, yes. So I wasn't sure how much time I have, so actually let me go in, because there are questions, let me go into some more details on this. So yes, the question is, what is the quality? Because we're doing a couple of things, right? First, we're going from a point set to a sparse similarity graph, and second, we're adding approximation. The interesting thing, and that was a big surprise to us, is the net effect of those two things where it was positive. It was not even neutral. So if you look at the plot here, so the y-axis shows the quality, x-axis shows the number of neighbors in our k-nearest neighbor graph. This line here is just an exact quadratic algorithm. We can see that quite often ParHack delivers better quality. And the explanation we have is that actually going from a complete metric to a k-nearest neighbor graph is actually a step that helps remove noise from the input. And so while we sparsify the input, we also make it an easier input for the clustering algorithm. And this is reflected by the increase in quality. Any more questions? Yeah, and then in terms of, since I'm hearing. This one?
So. Can you explain how you actually calculate similarity of the failure?
Yeah, so this is the, and that's a great question. So we have a K-NAND graph which has distances. For this algorithm, we want similarities. We played with several formulas. Not sure what was the one we settled on, but it was things like 1 over 1 plus this similarity is 1 over 1 plus distance, or things like that. It's not very principled. We have to settle for something, and we compare several options.
Because my question, like why I asked this question is because you were saying that you don't know what's the global objective that you're like maximize the right thing. Well, and when I think about it, one of the reasons for this, the similarity is right, you use the notion of similarity where one make it better, right? It's the ones that
Yeah, we also normalize to 0, 1.
Yeah, exactly, right? But I mean, like, if for example, if you wouldn't use the notion of similarity, that is the bigger the better, but the distance, right? Which actually is somehow intuitive style, right? Then basically the algorithm is somehow trying to see a link with like Russell algorithm for Steve, right?
It's very similar to MST if you don't use average linkage, but single linkage.
Exactly.
Similarity between clusters is the maximum. Like with average, I'm not sure with the connection.
So now my question is like, is it possible that you can maybe like actually don't you can like use some different notion of similarity so that average linkage that would be equally good when it comes to results, but at the same time you have the global objective. Like awesome.
I think that's a fantastic question. I do not know the answer, but yes, I do think this is a good linkage function. It's not, it probably can be improved. And if you can couple this with some theoretical results, I think that's very interesting. Yeah, I would study. Now, one comment, why do we choose similarity and not distance in the algorithm? I mean, we could, in principle, we could define this on distances. The issue is that we need to define how to treat non-edges. With similarity, we can see that non-edge has similarity 0. If you use distance, the non-edge would have to have some large distance, and it's not clear how to do that.
Just a little related to this. So the metric info, it's showing difference or similarities.
The metric, it depends. You can have some, in some cases you have Euclidean distance. In that case, the metric gives us just distances. If you have L2 normalized embeddings, You can also do cosine similarity, so just complete dot product. Then you naturally have similarity in that case. So like if you have L2 normalized points, then like essentially dot product gives you the value similarity. Euclidean also gives you one of the two are like essentially monocle each other, virtually monocle. Yeah, so since we're here, just a couple of I know it's unrelated, but I wanted to show what's possible with efficient implementations. So we did test or have done several graphs. We also had like a simpler algorithm, affinity clustering. So Hal knows a lot about it. We tested on graphs of up to 100 billion edges, and then for PowerHack, the running time was about 3 hours. We also have a version of affinity clustering that can handle this clustering this graph in about 10 minutes. So we have two options that can interpolate between different running times in this regime. But this also means that there is a lot of potential headroom. Like a reasonable clustering algorithm is still orders of magnitude faster than PowerHack, which means that we will probably still work on like coming up with a faster algorithm. All right, let me go back to where I was. I think the jump there. Okay, sure. Okay, yes. So that was PowerHack, shared memory, efficient, but still limited by single machine RAM. And now, actually, the space available in a single machine is probably the single most limiting factor for running algorithms on large data sets. So the fact that this algorithm is designed for a single machine is limiting in terms of scalability. It also runs few thousand rounds in practice, which makes it difficult to like naturally translate it into a distributed environment. So settings like MapReduce, Hadoop, and so on. So a challenge is how to give a hack algorithm that can use a low number of synchronization rounds and still guarantee a 1+F approximation. And for that, we introduced TeraHack, which is yet another way of implementing the average linkage hierarchical agglomerative clustering. This part is going to be, I would say, slightly unsatisfying in the sense that we'll have an algorithm that has a provable guarantee on the quality, but we would not really have a guarantee on the running time. I think it's actually an excellent question to how to analyze the running time of this algorithm that I'm going to show in the next few slides, or some variant of it, because the algorithm is going to be more like a recipe for playing algorithms in the distributed setting. So what is the starting point? The starting point is the following algorithm, which is actually the algorithm that I mentioned that obtains the n-squared running time in the metric space. This is an algorithm that runs exactly the exact hack, even though it's probably not obvious that it's computing the same thing. So let's start with the definition. We say that the merge of two clusters or two vertices in the graph is good if one is the most similar neighbor of the other and vice versa. So basically for each vertex, we mark an edge to the most similar neighbor, and two vertices that point at each other are called a good merge. And now consider the following algorithm. While there are at least two vertices, we find and perform all good merges. The surprising thing is that the dendrogram this produces is exactly the same as the dendrogram produced by the exact average linkage time. It's actually true for any linkage function that satisfies a certain condition called reducibility. So I think it says something like if you have a vertex A and vertices B and C, and we merge B and C together, then the new similarity you obtain is less than maximum of the two that you start with. For any linkage function that satisfies this algorithm computes the exact result. Now you can see that good edges, they also form a matching if we assume there are no ties between the weights. So this is actually a reasonably easy to implement parallel algorithm, except that it doesn't really have any bound on the number of rounds. So that was known. And now what we did we're able to combine this idea with the notion of approximation to obtain an algorithm which is, it's more parallel empirically. It's actually something we cannot yet capture theoretically, and again, I think it's an interesting problem to study. So the main idea here is the following condition. So if we have two clusters, we say that the min m of a cluster is the minimum merge similarity that was used to create it. So when we have a cluster, it was obtained by some merged clusters. We just look at the minimum of the similarities that we used in the process. So for a cluster of size 1, this is just infinity. And if we denote by max W of C the maximum edge weight incident to C, we call a merge 1 plus epsilon root when the following condition holds. So the maximum of all the edges incident to these two clusters divided by the similarity between them and the minimum of that and the minimum merge similarities has to be at most 1 plus epsilon. Now you cannot see, well not see, you can prove that these two things vanish when epsilon is equal to 0. This also vanishes, and this simplifies the algorithm from the previous slide. So it's really a generalization of what I showed in the previous slide to the case of 1 plus epsilon approximation. And we show that if we apply those good merges or 1 plus epsilon good merges in any order, you obtain 1 plus epsilon approximate hack algorithm. What this means is that any output of this algorithm can be obtained by some run of the 1 plus epsilon hack algorithm under some choice of merges. That initial algorithm is given freedom, and the output of this is within the output of that. So now what is the TeraHack algorithm? Again, we start with clusters of size 1, and then we will partition the graph into these joint clusters. Here the goal is to have pieces of the graph that fit in a single machine. This partitioning for correctness is entirely arbitrary. And now we will apply 1 plus epsilon with merges within each cluster as long as possible. And then after that, we're going to gather all those merges together, apply it in the whole graph, and start it around. Now note that this is actually is correct in the sense that if you have two disjoint pieces of the graph, you apply a good merge in one, you cannot affect whether a merge in some other piece of the graph is. Yes.
You partition the vertices.
Yes, you
So
partition
that are internal to the same cluster, like your same like your chain.
Yeah.
Then just between clusters, so like
so you actually edge between two clusters needs to be set to both clusters because the definition of the good merge uses incident edge of two vertices.
Okay, because you have to take that into
You have to
decision
take-
that it's like a maximum or something, but you never like.
Yeah, you never merge them. So they solve as like safeguards, saying they tell you, okay, now they may actually stop you from making too many merges, and they
Right, but then the merges are already inside the machine. Only between vertices are the same.
yeah, exactly. Yeah, and then so when this is run inside each cluster separately, they emerge in one cluster cannot make the emergent in one other cluster bad. So this can be run independently. And now for the unsatisfying part, we do not have a proof of like the run complexity of this. I mean, of course, this was a bit underdefined with all the partitioning, but even if we run a strategy like that without partitioning, it would be very interesting to see whether we can somehow bound the number of rounds that this approach gives. Empirically, it's like the number of rounds that this needs is much better than in the case of Hierarchical. And we've been able to run this algorithm on very large graphs. So here you see the number of vertices maybe like maybe a dozen or a bit more. And then Hierarchical it was like that. Now we've been able to run it on very large graphs. So this is quality on a graph of 8 trillion edges and like say 30 billion vertices. Quality here means it's with respect to a set of 60,000 labeled pairs of vertices. So they were labeled by human raters, whether the two endpoints should be in the same cluster. The specific data set here was, I think, web search queries that we were clustering into clusters of the same meaning. And as you can see, TeraHack is delivering a better precision recall trade-off over the SCC which was essentially the state of the art before work. If you're wondering how important this improvement of like few recall points is, I can tell you it is important. I mean, for those type of applications, large scale applications, even a single percentage increase in the quality is noticeable downstream. Okay, so now let me start summarizing. What are some interesting open questions here? So first, the question is, can we run hack and adjust a single logarithmic number of rounds? Hack the number of logical rounds was log squared roughly. It seems that TeraHack is running faster than that. Possibly by merging some of TeraHack and TeraHack ideas, you would be able to prove a logarithmic bound on the running time. Even, let's say, even in the shared memory problem setting where we don't have to do this partitioning, because that part is not even clearly defined. Another interesting question is how fast can we run hack dynamically? It's also very common in application that we cluster the same data set all over again with some minor changes. Now, there is a lower bound saying that even if we allow approximation, the update time of an algorithm has to be at least polynomial again. I mean, this one is of course like less than 1. And in particular, the square root m time for update is not ruled out by this lower bound as far as I understand. So I think this is an interesting avenue for stuff. Another thing I would like to mention is a general comment on like how we choose problems to work on in both communities. So the theory, I think that what we focus on a lot is obtaining good asymptotic writing time and low approximation ratio. We also want an algorithm that can be described in 100 pages so that you can write it down and submit to a conference. Now, in practice, there are like many more nice to haves that an algorithm can have. So you want to have fast writing time in practice, and constants do matter. You want to have essentially 1 plus epsilon approximation. So it's extremely common that like a simple heuristic goes very close to optimum. And so if your solution is twice worse than the optimum, it's very bad in application, and it's also and it's actually something that's probably not going to be too useful. I mean, of course, I'm making a general statement, but this is common across, like, say, clustering problems and several others. I'm sure there are exceptions to what I'm saying here. Now, we would like an algorithm that are not just efficient when n tends to infinity. Our data sizes are limited, and so we need to look. Sometimes looking at just the sometimes notation is not too useful. We want to have a simple algorithm. There is this amazing correlation of simplicity of an algorithm to its practical applicability. Space usage is extremely important. As I mentioned, this is probably the #1 limiting factor for scalability of practical algorithms. So, for example, removing a log factor in a space usage of an algorithm is going to allow you to run it on like 10x larger data sets. And I think that's again something that's not going to. You want algorithms that are easy to implement, test, and maintain. This is also, just for practical considerations. And there are many others. I mean, the list can go on. Now, my point is that I think as a community, we focus a lot on those benchmarks, but in many cases, they're just proxies for what's happening on the right-hand side. And I do think that there's a lot of algorithmic challenges that open up when you take this view and you start to think about algorithms that satisfy lots of those desiderata on the right-hand side. So yeah, I encourage you all to look there. I have found a lot of inspirations. So now let me really sum up all that I said. So hack is a great algorithm that can be implemented in roughly n to 1.5 pound on sparse graphs. Most likely not faster, but if someone proves me wrong, I will be very happy to. There's actually one other question that I just remembered. can you beat this bound in, for example, in the case where your graph comes from a matrix, from point in a matrix space? So for example, if you assume that your graph is a k-nearest neighbor graph, can you do faster than this bound? We don't know that, and that would be a very interesting and well motivated result. And now inserting approximation into hack, as I mentioned, can lead to near linear, parallel, and very large scale implementations. It's not possible if we want, well, parallelizing exact hack is most likely impossible. And then we were also able to come up with efficient implementations of these algorithms that can scale to 100 billion at graphs on a single machine, creating trillions of values in multiple machines. And that's all I've got. Thanks a lot.
Thank you.
We have plenty of time for questions.
So what's the simplest problem that you can think of solve in theory, but it's unsatisfactory?
Simplest problem that's solved in theory, and
That's all the it has all the other features that you mentioned. That's it.
Okay, that's an interesting question. Well, when you say the simplest, then it's not easy for me to come up with an example. What is that?
Simple.
Simple. I'll have to think about it. I mean, one of the examples I like to give as to illustrate this disconnect is correlation clustering, where it's maybe not that we don't have to do practical solutions, but all the practical algorithms for correlation clustering that I know don't use any of the problem structure. So there was a lot of theory study of correlation clustering, which naturally means that we understand the structure. Now in practice, we just use locus, like some, and without proof. So this is just to illustrate like that there is some work that can be done in between. I know that there is someone talking about bridging this gap, and I was super happy to hear about that. So maybe this comment would become obsolete to some point with some bugs that come up. I would happily think about more examples. I was before this I cannot think of stuff of the top of my head. Yes.
If you consider instead of everything something like the single link, those algorithms for distributed minimal spanning tree, would they solve the problem in terms of the number of rounds that you are interested?
So generally, yes. Actually, in the case of single linkage, recently, actually, in the paper. This paper is actually giving a parallel algorithm for single linkage clustering. This is like from spot 22. Now the challenge there, it's almost like doing MST, except that even you have MST going from MST to dendrogram is not entirely obvious, and this is what was happening here. But I think in that case, grouped parallel algorithms are already. Yes,
You would just run an algorithm on the correlation clustering instance. How would that be in terms of correlation clustering?
You're talking about unweighted, right?
Yes.
So yes, I mean this algorithm is not like the greatest for unweighted instances because the first thing it's gonna do is it's just gonna merge a random edge. Each edge is equally good. I think that there are some connections between what correlation clustering is doing and this algorithm. We haven't been yet able to formalize them, but there is like both for correlation clustering and for this algorithm, you can show some kind of bounds on the density of each cluster that you find. Once you find it. But the question is, I think what you can't maybe easily guarantee is that every dense cluster will be found in some sense. So there are some weak connection between them. We're actually looking at some of the different projects.
Question in chat.
Two questions. In that lower bound for n on one public time dynamic type, what is the approximation factor? What was that constant for any finite? I do not remember from the top of my head, but I remember it was surprisingly large. So I think it's.
Okay.
Okay, I don't wanna make guesses, but I think it's at least a large constant it will come. Second question. The question here is for each level of merge. Is it possible to consider some non-uniform version of hack approximation? Maybe the merge should be more precise in the flows to the loop, but can be more relaxed going down to the leaves. Yes, I think that's useful in the sense that, I mean, that's a very reasonable notion. It was not needed really for the static algorithm. I mean, we were able to obtain efficient algorithms without that. What this may be useful for is maybe this is another way of bypassing the hardness for dynamic hack, which is pretty large. And yeah, coming up with a slightly different notion that will allow us to dynamize the algorithm would be certainly interesting.
Okay, thank you.
Thanks, Jen.
And so I just want to say that there's a paper uploaded 4 days ago which claims a subcubic combinatorial time architecture. So
Okay,
that might
amazing. Okay, so now, yeah, we can speed up hack, it seems. Any more questions?
Okay, in that case, let's thank the speaker again.